Okay. I'll stop recording.
Hello everyone. Welcome to day 3 and the second class, and hope you enjoyed the first one. This one will be taught by Rushil Mathur. Rushil is an 18-year-old. He's currently pursuing his undergrad studies in Oxford, and he's a really fun teacher, and so I'm very excited for the class. And he's an IMO gold medalist from this year, and also an APMO. Something I forgot. Something you had, and yes, he's a what else? He has written a book. Yes, I cannot forget that. Check out his best-selling book,
The promo is necessary.
Investigation of Olympiad Combinatorial. It's almost always out of stock on Amazon.
It's not been out of stock for a while now. That's quite impressive, I think.
Damn.
That's great feedback.
Yeah, so you do check out the book. Very fun book.
I don't know if that's good or bad though, because that could also mean that no one's buying it. Okay.
It
Anyway,
could mean that somehow it's found its way on lib.
no, but I think we
Yeah.
just put 200, 300 copies in one shot. That's why it's not been running out. So anyway,
I see.
let's screenshot. Okay.
Yeah.
So combinatorial Nullstellensatz. The hardest part about this entire topic is learning how
Wait,
to.
first thing, how do you pronounce it?
Good question. So for sanity's sake, we will never pronounce it. Instead, we will always say
Oh no.
null. This is the safe thing to do in life. Like don't like take too much panga with such long words. Okay. Now an interesting thing about combo null is that when you look at a handout on this, usually you will stop reading it 2 minutes into it. At least that's what happened with me. The only time I finally ended up learning it was a lecture by Shantanu at IMO TC that actually made it make a lot more sense. Um, the point is there is a little bit of weird fancy notation, like people start by defining what a field is and stuff like that. You don't really need all of that. This whole area is defined basically as an extension to this whole idea that if you have a polynomial p of x and it has, let's say, real coefficients and it has degree d, then it can have at most d roots. Unless it's the zero polynomial, but then I wouldn't say it has degree d. So I don't know whether that's an exception or you want to take that separately, but whatever. The whole point of combo null is now we think of this, but in multivariable polynomials. So let's say, just to start off, let's say we have only two variables. So like p of x comma y, and we'll have to be slightly careful about whether this is an integer polynomial or a real polynomial or a polynomial with coefficients mod p or things like that. So what people do in general is they say, so they use this notation, it belongs in a field with these two variables. So you don't need to worry too much about the whole field thing. It's basically some place where you can add, subtract, multiply, divide. So for example, real numbers works out. You can also take integers mod p because there you can multiply and divide. Of course, you can't divide by 0. That's the only rule. But apart from that, things work out there as well. So we won't worry too much about that. So just think of it as some polynomial with coefficients in some set, something like that. And now the question is my net bad or is other like
No,
I
no,
think it's
I also.
others.
Adit, sorry, your net was lagging a bit. Did anyone catch what he was saying?
No.
Okay. We'll come back to him once, or maybe you can send a message in the chat. I should keep checking chat. Okay. Anyway, so p x comma y, the point is that we want, p of a comma b to be non-zero, essentially. So here what you would do is you define a set, let's say a set of d plus 1 things. So let's say 1, 2, 3 till d plus 1. And then what you can claim is there exists
By the way,
S.
is a field defined only mod prime or it can be mod anything?
Yeah, mod n is not a field because weird things start happening.
Mod
Because,
1.
like, for example, 3 into 5 is 15. So if you have a mod 15 field, you would have two
No,
things
like
like that.
I asked like because suppose you have field model, then you can't divide by anything that has GCD with.
Yes, exactly. You can't do that. So it's not a field. You have answered
So
your
you
own.
can just you can
Yeah.
say mod 1 is a
In
field.
fact,
Like
the rule I
the
think is that you can have a field of a size. If it's finite field, then the size has to be a power of a prime. That's something you can spend a lot
I
of.
think like see, infinite fields is a different thing. If you care for finite fields, just think of FP. Other fields are a bit more complicated. They are not modulo something. They're more complicated. If you want to think simple, just take mod P. That
wait.
just work over FP, which is integers
Actually,
mod P, which
we don't
FP
even
is a
care too
prime.
much about finite fields. Just think about like real polynomials whenever you're confused. Like we will
Yes,
be
just
using
think
some
about
problems
that or
where we
FP.
will have, yeah, we will have some problems where we'll have mod p, but you can still think of it as real things. But in your last mind, just remembered, oh yeah, they were coefficients from 0 to p. Coefficients don't matter here. Um, So the point here was there exists some number in this set such that P of S is not equal to 0. So this is what we could have claimed earlier. And now we're aiming to generalize that. So what we'll say is we'll define two sets, S1 and S2. So basically X can vary in S1 and Y can vary in S2. So basically, let's say you define some 1 to T1 plus 1 and 1 to T2 plus 1. So these don't have to be literally the numbers 1, 2, 3 till T1 plus 1. These just have to be T1 plus 1 different numbers, but it doesn't really matter. So I'm thinking of it like this. And the claim then will be that, given the right condition on Px comma y, there is, of course, the basic condition that the degree has to be at most T1 plus T2, but you will also need something specific. So we'll talk about exactly what we need. But the claim basically will be that there exists some a comma b belonging to S1 cross S2. So some choice from here and some choice from here, such that P of A comma B is not 0. And the magic thing about combo null is the first word, not the fact that it's Nullstellensatz, who is just the person. No, anyway, like the point is that it's used in combinatorics problems. And the usual hard part of the problem is not understanding, what to do with the whole theorem. It's understanding how do you convert your combi problem into this polynomial. So we'll talk a little bit in
Isn't
detail.
that for every combi problem like graph theory halls?
Yes, that's true. In fact, with a lot of Olympiad things, like the hard part about Olympiad things is always finding that middle step, like finding out, do you need to convert this into polynomial, into graph theory, do you need to add a new point in the geometry thing, like anything, like always these middle steps are what makes Olympiad problems interesting. But yeah, whatever. Um,
Wait, can you repeat what exactly combo null is? Like, I think
so
I missed it.
Combo null, we have not actually defined anything. We're just saying the idea. The idea is that you want to generalize this idea that a single variable polynomial can't have too many roots to multivariable polynomials. So now if it has two variables, then it can't have like t1 plus 1 into t2 plus 1 such roots. Even though, the whole thing is multivariable polynomials are very weird. For example, if you have pxy as x minus y, this has infinite roots. Like anytime x and y are equal, the root is there. So you can't anymore say that it has finite roots. For example, any degree d single variable polynomial has finite roots, but that's not true here. But if you choose your sets in interesting ways, so that you take every pairwise thing, then somewhere in that pairwise thing it will be non-zero. That's kind of what component says. But we'll not what if non-negative coefficients? Integers in general don't work too well with this because you need to be able to divide. um oh, non-negative, maybe you meant r plus. That's not fine because you can't subtract well. So you need to be able to do everything. Yeah. Okay, so yeah, so let's actually look at a problem. So we'll try to gain some intuition by looking at a problem. Let me get a screenshot of the problem. Actually, that'll be cleaner. Okay, so this is some random Russia problem, and obviously using combo null will be an extreme overkill because I don't think that's what was intended, but we will do it anyway. And we notice that we don't actually know what combo null is as of now, so we will kind of figure it out. But the idea is, what is really going on. So here you have like these 100 numbers on a circle. So like you have like these things, and on each spot you have two options. So let's say here your options are 1 and 2. Here your options are 2 and 7. Here your options are 1 and 8, etc. So on each thing there are two numbers written. You have to choose one of these two numbers. Oops, probably don't annotate. Okay, I guess I'll just let that stay. You have to like choose one of those two numbers. So let's say I choose this and then I choose this, but I want any two like adjacent things to be different. So here 1, 2, 1 are all different. But for example, here I could not have removed this because then both of these would be 2s. Yeah, so alternating sequence is ideal. In fact, this is important that 100 is even, so you can kind of alternate. Because if you had a 99 gone, then if each spot they gave you 1 and 2 as your only two options, then what you would have to do is 2, 1, 2, 1, 2, 1, but on this side you would get 2, so there would be a contradiction. So 100 is kind of actually relevant here.
Okay, first we can say that if we have a method for n different values, we have a method for n minus 1 different value for n different values, then we have a method for n plus 1 different values. Right, so if we have shown that we have a method for 2 different values, we are done. And then we can find a method for 2 different values. And for 2 different values, it's quite easy what the method is.
No, wait, are you saying in all take the superset of all possible things across all of these things?
No, I'm saying that if we'll show that if we have a method assuming n
It's
different numbers,
like
we can have a method assuming n plus 1 different numbers.
induction.
What are these n different values? Are they at a single vertex or across everything?
Across everything. Like if there are
Okay.
n different values across everything, we are done assuming with n plus 1 different values. Right? Because we are less restricted in a sense.
So that's the intuition, but
So
that's
that's
hard
good.
to say formally, right? Like, I mean, it's not obvious that having an extra option overall will help you in the long run
It
because
is obvious because having extra option.
no, because for
cannot-
example, I'll show you, right? Like, let's say there were 5 options, out of which you're going to say, I'll just ignore one of the options. But then if you just ignore one of the options, let's say this had 1, 2, and this also had 1, 2.
No, I'm
and
not saying that. I'm saying if we have a method for 4, then we have a method for 5. I'm not saying the right ulta.
If you have a method for 4, then you have a method. What is the method for 5?
Yeah, right. So I'm saying that basically, let us say we have a circle and we have all the numbers from 1 to 4. And then we are saying that some of these numbers are replaced by 5.
Okay.
Right. And so that is what. Sorry. Yeah, we can for any actually what we can do for any of these 5 ones, right? We can just replace 5 by 4, or because let us say on a set we have the numbers 2, 5.
Okay. Also, I'm going to stop this a little because there is a simple solution that works, which you like basically you take 2 elements, induct those kind of things.
Yeah. And
But
so we can
the
take
whole point of this whole thing is that we're not bothering with that. We're just trying to understand what combo null would say on this problem. So I'm going to like look at something totally like different from what you guys are saying, just because that's the idea which will be used on a lot of problems, but there will be no other solution. This is more of like a jokey example. So let's say your two options here were A1 and B1, and you chose X1 out of those two, and then you chose X2 out of A2 and B2, and so on. So think about it like this. So X1 minus X2 into X2 minus X3 into X100 minus X1. Essentially, what you want to ensure is that you can choose xi belonging to ai comma bi such that this thing is not 0. Because if this thing is not 0, then that means x1 not equal to x2, x2 not equal to x3. So basically none of the neighbors are equal. And the question is, given that S1, so it's kind of a polynomial in 100 variables, and S1 is like the set A1, comma B1, where these are the two options given here. And the point is, for each of these variables, you can choose any of those two things. And all you want to ensure is that the polynomial is non-zero. Degree of, so yeah, so we'll talk about, whether, it works or not, but this is what we want, right? Does it make sense? Like, you basically want x1 not equal x2, x2 not equal x3. And this is a very common theme that will come up in the whole lecture. Whenever you want a lot of things to be true simultaneously, you kind of multiply them. So basically, for example, let's say you want to check if a number is 0 mod p. So there's this very funny trick which you can do. You want to check if x is 0 mod p. You can do something like x to the p minus 1 minus 1. So if x was 0 mod p, then this would be non-zero. In all other cases, it would be 0 mod p. So like you do these sorts of kind of manipulation tricks or whatever you want to say, just to make sure that what you want is non-zero if and only if the condition holds.
Kind of
And
converting something into a more solvable way of solving.
yes. So now let's actually get into what is the statement of component. So the first thing we'll say, so claim 1 is that if you have so we'll define these sets, right? S1, S2, and we'll define that the polynomial is in n variables. So okay, I'll just say x1 to xn, right? So n variable polynomial, and S1 is the kind of the range of things that x1 can take, S2 is the range of things x2 can take, and so on. So we'll define S1 to be t1 plus 1, and the motivation for doing the plus 1 is basically the same as why there were d plus 1 things in a degree d thing. So it's kind of the same idea. And you have Sn having tn plus 1 things. And the point is that, okay, so the first claim is saying that if you think of this polynomial as a polynomial in only x1, so if you think of px1 till xn as some polynomial q of x1, then its degree is at most t1. And if you can do this for each variable, so basically the degree in each variable is at most ti. So degree in xi is at most ti. If this is true, then as you might expect, there will be a non-zero thing. Or px1, x2, xn is itself the zero polynomial. So the point again is that like, okay, so yeah, let's try and prove this now. So this is actually not that hard to prove. We're basically going to just try and induct. The idea is that, okay, we'll just do it for two variables and then you can see how it happens in general. So if you have p of x comma y, and you know the degree in x and you know the degree in y is like degree in x is at most t1, degree in y is at most t2. So you can think of this, so you can think of px comma y as summation. So I'll define r I y x to the I. I is from 0 to t1. So basically you're thinking of this as you're grouping terms by common factor of x to the power that, and then you're grouping the whole y thing. So this riy is just some polynomial in y. So just to give an example, let's say you had the polynomial x square y plus xy cube plus x square y to the 4. What you would do is you would say this is x square times y plus y to the 4 plus x times y cube plus 1 times 0. So this is kind of like, these are your three ri's, r1, like r0, r1, r2, and this is your powers of x. Does that somewhat make sense?
Could you please repeat what are the T1s are? Like on the
Yeah, so T1 is just some number, so that we know that the degree in, so the max X coefficient you ever get is T1. Like we know that. That's given.
and what is
Alright.
the S1, S2?
S1, S2 are sets of numbers, so that we want at least something in the cross product of S1 cross S2 cross Sn to be non-zero. P of that to be non-zero. Like we'll come back to it. For now, let's just look at this. Yeah, someone was saying something?
Ri of y is an arbitrary polynomial, something like that.
Yeah, Ri are just some polynomials based on what P was. Like P uniquely defines Ri, but we don't know what Ri are before that. So now the interesting thing is that if let's assume that whenever you take so if you ever so if you ever have x comma y belonging to S1 cross S2, where S1 has T1 plus 1 things and S2 has T2 plus 1 things, let's assume this is always P of x comma y is 0. So we'll kind of, prove by contradiction kind of thing. So we'll show that this is a 0 polynomial basically. And now the idea is that, you can fix your y. So fix y as some b. So y equal, or let's just say y equal y naught. And then what you're saying is that this is a degree T1 polynomial in, so now these things are just constants, R1 y naught, R2 y naught, R3 y naught, etc. But in terms of x, there are T1 plus 1 roots, because even though y is fixed in the set, S1 can be like, x can be anything in the whole set of S1, right? So essentially, just to give an example again, like let's say T1 was 2 and T2 was 3. Then let's say you have 3 possible values of what T of for this, and you have 4 things here, 2, 6, 7, 8. So what I'm saying is you fix one thing from here, 2, right? And then what you would have here is you would have R1, 2, R2, 2, R3, 2, R4, 2, etc. And that would just be some polynomial in x. So you would get some qx, which has roots at 154, because we have assumed that at every cross thing of these, the value is 0. So basically q1 is 0, q5 is 0, q4 is 0. But the degree in x is 2. So it's like a quadratic polynomial which has 3 roots. And that means that it's a 0 polynomial. So what that is telling you is that R naught y naught is 0, R1 y naught is 0, all the way till R T1 y naught is 0. So basically all the coefficients have to be 0 when evaluated at y naught specifically. So if you plug in y naught here, then this becomes a 0 polynomial. But also, if you plug in y1 here, where y1 is also something in your set, so R naught y1 is also 0. Similarly, R naught y2 is also 0. And so in general, what you'll get is you will get a bunch of things here, and this will be a bunch of T2 plus 1 possible values of y. But this R thing, the degree of this can be at most T2, because we had assumed the degree in y is at most T2. The max power of y you ever get is T2. So the max power here is T2. So basically what that would force is that R naught itself as a polynomial, not just evaluated at these points, but always, R naught y is always 0. Like it's just the 0 polynomial. So what that means is that this is just the 0 polynomial x naught plus 0 polynomial x1 plus blah blah blah. This is just 0. Does that kind of make sense?
Could you please repeat the last argument once again?
Yeah. So does it make sense that R naught y naught is 0, R1 y naught is 0, and all that?
Yes, that part is clear.
Yeah. So that is true for any y naught in your S2. So in particular, you have that R naught of anything in S2. So I'll just write R naught of S2, which is kind of bad notation, but this. Basically, R naught of anything in S2 will evaluate to 0. But R naught itself is a polynomial in Y, which has degree at most T2, because we had assumed that the polynomial, the degree in X2 is at most T2. So in any variable here, the max Y degree will always be T2. But there are T2 plus 1 things in this set. So what that implies is that the R naught polynomial itself must be the 0 polynomial, because it has more roots than variables.
So
So
what did we contradict exactly?
so yeah, kind of what we have assumed is everything in S1 cross S2 is 0. And what we have shown is that the only way that's possible is if we started off with a 0 polynomial. So the
Okay.
So I
claim,
think
so the exact thing
in
is
this case,
basically,
through induction we can prove it for general.
yes, exactly. So now if you have P, X, Y, Z, you think of it as a polynomial in X anyway, but now your Ri are kind of like Ri, Y, Z. And then now you say that, by our previous case, because whenever we had two variables, you could make this non-zero. So, you kind of induct in that sense. We won't go into the exact details, but this is just I mean, now it's pretty clear as to how you want to extend this. This
Then
is not a statement
T1
of combo null though.
polynomial,
Sorry?
then T1 polynomials, those T1 polynomials, we need to prove that they are also 0.
I didn't get you.
Means the polynomials Ri, Yi are all 0.
Yeah, all the
They are
Ri, Y
at
polynomials are
one
0. That's what we
degree.
proved. That's what we proved. R naught Y is 0, R1 Y is 0. All of them will work out in the exact same way. So
P,
this,
P, P of x comma y will also P of will be also 0.
yeah, P of x comma y will happen to be 0 x naught plus 0 x1 plus 0 x to the t1. So it's P of x y is always 0. So yeah, basically what this is saying is if all your degrees in every variable is kind of small, then you can't have so many roots. Like you can have infinite roots. So for example, that x minus y, you can have infinite roots, but you can't have like, this is a root, but like kind of like a net. So every pairwise thing here is 0. That is unlikely. You can have a lot of independent things, but you can't have lots of things that overlap.
So the
That's
degree
kind of,
must be greater than Ti.
yes, yes. Degree in something would be at least. Now let's come back to this problem. So basically here what we have is that each Ti is 1 because there are two things. So Ti plus 1.
No, Ti is
What we
2.
would, hmm?
Ti is 2, right? X1 into minus X1.
Yeah, that's the problem, right? What we would hope is that here the degree of each thing, degree in x1 is at most 1, but actually the degree is 2 because you have x1 from here and x1 from here. So that's kind of terrible. So this is why this is not actually a combinatorial Nullstellensatz, because this is not very strong. This is kind of something that, it's not groundbreaking. Combo null kind of says, so this is the actual statement. So you can forget about most things, it says. So it says that if I'm just trying to, okay. So basically the idea is you don't care about the individual degrees anymore. All you care about is, wait, I'm just checking if you even need one particular constraint. Yeah, you do need. So yeah, all you need is that the total something works out. So um, if P of x1 to xn has degree t1 plus t2 till tn. So basically, if you add up all the degrees of all the variables and then you look at the degree, then it should work out. So you don't need the individual things to be at least at most t1, at most t2, at most t3. You just need the total sum to be at most tn. So for example, here, each ti was 1, so the sum of the degrees was 100. And here also the sum of the degrees is 100 because each bracket gives a degree of 1. So that kind of thing is actually pretty useful. So even though the individual degrees are going up to 2 sometimes, but they're also going to 0, so that kind of balances it out. But this is not it. There is more to this. If this has degree T1 to Tn, and now this is a very important concept. So this is the only thing that you really need to think about when you apply combo null. So what it says is that coefficient of x1 to the T1, x2 to the T2, xn to the Tn not equal 0. So this is kind of random looking, and we'll see where this comes from. So basically, if this is true, and you take S1, oh, should not use a marker. And now you do the same thing. So you take S1, S2 till Sn. This has T1 plus 1 things. This has Tn plus 1 things. Then there exists x. I'll just say y1 till yn belonging to cross product such that p of blah is not equal to 0. Does that make sense? So this is kind of the same thing as the previous one. So again, we're saying p of that thing is not equal to 0 if you take the big sets. But now you don't need this constraint that degree in xi is at most ti. All you need is that the total degree works out, which will almost always work out. And coefficient of x1 to the t1, x2 to the t2, xn to the tn is not 0. Now the question is, where is this coming from? Basically, what you want to do is, if you ever okay, so again, I mean, I won't do the exact details. So again, for starters, we'll just think of two variables, and there'll be some things that will be slightly left over, but the main idea here is basically that whenever you have something like x1 to the t1 plus 1, so okay, we know that whenever whenever x belongs to S1, we know that x minus S1 till x minus ST1 plus 1. So S1, S2, S3 are the, okay, this is bad notation, but basically assume that these are all the elements of this first set. So basically, whenever x belongs to this set,
Here.
this is 0.
What is this here?
Sorry, this should have been x. Maybe I can fix this. Should use a maybe. A1 till AT1 plus 1. So here I'm defining A1 AT1 plus 1 as S1. Does that make sense? So this product is 0 whenever x is in the set, obviously, because x is one of these things, so works out. Now the point of that is that this kind of tells you x to the t1 plus, like if I just expand this polynomial, so x to the t1 plus 1 minus sum of coefficients x to the t1 plus something 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 is equal to 0. So the point is, x to the t1 plus 1 can be described in terms of these other things in some vague sense. So basically what you do is, now whenever in if x had a degree greater than t1, so we're kind of going to try and reduce it to this case where the degree is at most t1. If it had a degree of, let's say, t1 plus 1, then we can rewrite this thing as this summation, because we know that everywhere on that S1 thing, it's equal to 0. So there's some details as to, can you do this? Does it always work out? You can think about it. I don't want to waste the whole lecture just talking about this. But the point is, basically, you can keep reducing the degree until this holds. And now the question is, why did we need this? Basically, the problem that can happen is that when you keep subtracting this, like let's say you subtract this stuff, but then you just ended up with a 0 polynomial. Like the only reason your polynomial was non-zero was because you had this sort of redundancy. As soon as you remove the redundancy, in the sense that you express things the way they can be expressed, it became the 0 polynomial, everything cancelled off. But it won't cancel off if you have this thing, because notice that this term can never get affected by anything you do, because everything you're doing is only affecting terms which have some variable to the exponent which is too high. This term does not have any such thing where the exponent is too high. So you will never touch this term. So the point is, at the end, your polynomial will still be a non-zero polynomial. And so you will be able to say that there is some cross thing where the polynomial is non-zero. So this was kind of confusing and a little bit theoretical as well. But does this kind of make sense? So our takeaway, it's okay if you don't have 100% grasp over the exact proof. You can also look at it later, like spend a lot of time thinking about it. But our main thing for today will be this. So if you have a polynomial in n variables which has degree t1 to tn and coefficient of that is non-zero, and you define these sets, then you can find some place where it's non-zero. Make sense? Like now is the time to speak.
Yes.
Okay. Someone is saying you
Messages
could
in the
repeat the
chat saying-
entire thing. What part of the entire thing do you want? Like, this was a very long entire thing. Like, this part I hope makes sense, right? This is kind of just like you're, like optimizing on things before. So, like, I'm not really too concerned about this exact thing, but this is just the statement that happens to be true. And this is kind of the idea of how that happens. Let's come back to this for a while and
Can you
see.
just show the statements once again?
Yeah, actually, what I'll do is I will take a screenshot of the like a LaTeX statement so that it makes you feel.
I had a question in the last part.
Yeah, go ahead.
We had shown that P of xy would be 0 in the last part.
This
Ye-
part?
Yes, yes. But then what do we conclude from that?
Yeah, so basically the theorem would say that if Pxy is not 0 and the degree in each thing is at most ti, and you take these sets, then you can find something in the cross product that is non-zero. Because what we did is we assumed everything in the cross product is 0, and we reached the conclusion that the polynomial must have been the 0 polynomial.
But like it couldn't have been the 0 polynomial.
Yeah, so it's a contradiction, exactly. So there must have been something in this x comma y which such that this didn't happen. Like this was a wrong assumption by us. We didn't make any other assumption. That's the only assumption we made.
No, but why P could not be the 0 polynomial? Like
It could be, but like for example, in our case, like when it's this, right? This is obviously not the 0 polynomial. Like this
Yeah.
is a polynomial. And in this, we need to conclude that if you put in some things, then the final answer is non-zero. So yeah, there will be three conditions we will have to check. If P is T1 to Tn, okay, the fact that the coefficient of this thing is non-zero already says that it's the non-zero polynomial. And then you have this. Does that make sense?
S1 was the number of ways of picking x1, right?
Yeah, S1 is the set of possible things out of which you need to pick X1. Yeah.
Okay, thank you.
So let's
Didn't
come.
understand the last thing you did.
The last thing I did, I also did not explain very thoroughly. So it's okay if you didn't totally understand it. The basic idea is that here the big constraint was, degree in xi is at most ti is a very strong constraint, which restricts how often we can use this. So we extended by saying that even if the degree was more than ti, I can use this sort of trick to reduce that degree without changing anything. And once I do that, then I will have this scenario again. Except the only thing I need to be sure of is that in the process of reaching this scenario, like starting at a polynomial and reaching this sort of polynomial, I didn't by mistake reach the 0 polynomial. So the way to ensure that is to have this coefficient being non-zero, because it so happens that in our whole process, we never touch this.
Okay, so like we wanted to get a polynomial because our original problem said that we have to have a polynomial whose entire thing is not zero. So we tried out things and found out that if it's the polynomial, if everything is zero, then the polynomial has to be zero.
Yes.
Then my question is like, why does it not conclude? Like, what's the weakness in that, and why did we have to use component?
Like the weakness is that this is usually not true, like degree in xi being at most ti. Like come back to this problem. Here your t1 was 1. So what you would need is that the degree in x1 is 1, but the degree in x1 is 2. So that's not good enough. Basically, it's all correct, but it's not good enough. That's the problem. It's a very weak statement in some sense. Whereas combo null is a more powerful thing, as we'll see now. Okay. Let's come back to this. Yeah, let's formally prove this now. So we take this polynomial in 100 variables. So p x1 till x100 is this polynomial, x1 minus x2 into x2 minus x3 till x100 minus x1. And we define set I, so the things in which the ith variable can roam around, as the two possibilities for that ith vertex. So let's just call them ai and bi. So the cardinality of Si is ti plus 1. So here ti is 1, basically. So now what combo null is asking us is we need to first check that the degree of this polynomial is 1 plus 1 plus 1 100 times, because the degree is supposed to be t1 plus t2 till tn. So let's check that. Yeah, degree is 100. Very nice, because degree of these things are all 1 individually. So that's fine. And the second thing is, what's the coefficient of x1 to the 1, x2 to the 1, x100 to the 1?
It's 1, I guess.
It's not exactly 1, because you can also
Two,
pick
right.
2 minus x3 minus x1. Yeah, but it's 2, because these minus signs also, there are 100 of them, which is very important, because if there were 99 of them, then you would get the coefficient is 0. So that's how, it all comes out so perfectly, because 99, this whole argument is supposed to fail. And this is where this part of the argument fails. So coefficient happens to be 1 plus 1, so 2, which is not 0. That's the important part. And so we can apply combo null. There will be something in the intersection of these sets, sorry, the cross product of these sets, such that p of those things is non-zero. So what that would mean is that this value is non-zero. So x1 is not x2, x2 is not x3, x3 is not x4, x100 is not x1.
Wait, shouldn't we first decrease the degree of each term?
Sorry, I didn't understand. What do you mean?
Like we have x1 squared, right? And
Yeah. So that's what we said, right? Like this is not good, but now we are using the strong statement where we don't need to reduce degrees. We just like work with. So
okay, yeah.
I didn't think I pasted the statement of combo null. I think I'll do that now.
Can you explain the coefficient argument once again?
Yeah, the coefficient. Do you see why? Do you want to see why coefficient of this is 2?
Yeah.
Like if you have each thing chosen exactly once, like you chose x1 from here, so now from these two you have to choose x100. So x99 minus x100, you have to choose x99, and so on. So basically, if you choose x1, then you have to choose the left thing in each thing. And if you choose x2 over here, then you have to choose the right thing in each thing. So there's exactly 2 ways in which you can do it, and the minus signs product out so that it becomes minus 1 to the 100, and you get 1. Does that make sense?
Yeah,
Like, I mean, if you have 3 variables, this should make sense, right? X minus y into y minus z into z minus x. If you want coefficient of x, y, z, it's like this or it's like this. That's it.
Yeah, makes sense.
But here it would be 0.
Is Si the number of possible values of Xi?
Si is a set. Mod of Si is the number of possible values of
X. Si is the set of all possible values that Xi can take, right?
Yes. So here Si we defined as the set of those 2 things which they allowed us to choose, and now we'll choose one of those by doing that Xi thing.
I had a question.
Could you just show how you would reduce the degree here?
No, we don't need to do the degree reduction process anymore. All we need to do is we need to check the.
No, like I get the common null states it, but could you just show how it's done?
Oh, so so you want the proof part of it then, right?
Yeah.
Yeah. So the idea is that because we are only concerned about things in S1, the point is that like you have whenever you're in S1, this equation is true.
Oh, okay, I see.
So you can rewrite x to the t1 plus 1 as the
Yeah,
summation, and nothing changes.
So
Okay.
what we had initially done is stack the proof for the two variables, right?
Yes, I mean, if you want to do this for more than two variables, then the idea is, okay, if you have three variables, you think of this as ri y comma z, x to the I, and then what you would get is ri y z is 0 for each thing, but then you use the inductive hypothesis that if you ever have a two variable polynomial so that it's 0 too often, then it has to be the 0 polynomial, so all of these would be 0. So the three variable thing will also be 0.
Oh, I see. So is this like, this is only the proof for combo null?
Yes, this is the whole proof of combo null.
Oh, okay, finally understood. Thanks.
Yeah.
Then
Yeah.
how do we like simplify, decrease the degrees for infinite sets?
Infinite sets we don't work with. All our sets are finite.
Oh, okay.
Like our sets have literally cardinality t1 plus 1, t2 plus 1, tn plus 1. These are all
Yeah.
finite. Technically, I think the statement says at least, like it just says more than ti, but then you can say there is some basic argument that okay, if you had more than t1 plus 1, then you can just get rid of some of those options and there will still be a non-zero thing. So it's all good. But yeah, this is the statement. So f is a polynomial in n variables in a field. Degree is t1 till tn. S1 to Sn are subsets of your field. So just some possible values, like real numbers, let's say, such that the cardinality of the set I has at least ti numbers. And there exists some thing from each set so that fs1 f. Okay. Whenever this coefficient is non-zero. Okay, let's
I
now
had a
do.
question from the previous.
Go ahead.
Yeah, so like x1 and x2 are like from the previous question. X1
Yeah.
and x2 are like both quadratic. So why are there like subtraction with degree 1? It should be degree 2, no?
Yeah, the degree is 2. That's why the original thing we made of this degree in xi being ty is a very weak thing. So now we don't actually anymore care about individual degrees. The only two things our combo null checks is the total degree being the sum of degrees. So that works out. Degree is 1 plus 100. So that's fine. And the other thing it checks is this coefficient. That's the only two things we are checking. We don't check individual degrees anymore. Because of this smart reduction we made, that we could think of x to the t1 plus 1 as this summation.
Can we strengthen the degree bound by increasing the domain?
What do you mean?
Like more than t1 plus t2 plus.
Yeah, that's what this thing does here. So a mod of si is just more than. Wait, I don't know.
I'm saying the opposite way.
Oh, you're saying the polynomial has degree more than this? Then you won't be able to say anything.
Okay.
Then it will become very suspicious, because then the one variable version of this problem itself will become false. Like if you just set t2 to tn 0, you would already have problems, because that can happen. Okay, so now let's look at the very famous IMO P6, which is kind of the origination of this whole topic in pop culture. Okay, so basically you have like this set of points in this plane, where all coordinates are 0 to n, but not the all 0 thing. So it's like everything in like this cube except this corner. So all of these points in not the whole cube itself, just the lattice points in the cube, if that makes sense. And you want to cover these points with planes. So you can choose a plane and you can place it like this. And you can place it however you like, but you cannot contain 0, 0 in any of the planes. But you have to contain all other points of S, all points of S in the plane. So the question is, what's the minimum number of planes you need? So if you didn't, if the 0, 0 constraint didn't exist, by the way, then what would the answer be?
It would just be like n plus 1.
Yeah, because you take the planes x equals 0, x equal 1, x equal 2 till x equal n plus 1. These are planes because, I mean, one variable is fixed or whatever. In general, you can think of a plane here in case you're not very familiar with three-dimensional geometry. You can think of it as ax plus by plus cz equal d. This is any plane's equation. And
We're taking the planes till x equal to n, right?
yeah, till x equal n. So in that case, there would be n plus 1 things. Give me a second. Yeah. So so you just have these equations, and a point lies on this if and only if ax plus by plus cz is actually d in that scenario. And okay, so yeah, can we find some sort of construction like in the thing
I'm
we said?
thinking like the diagonal-ish, something like that.
Yes, that does work. So you are saying something like x plus y plus z equals 0, x plus y plus z equal 1.
Yes, yes.
Something like this. So you could take this, no, not equal 0, sorry, start at 1, not x plus y plus.
From
Yeah, you
1.
start with 1 and you go till 3n. So this is 3n things, and that's a construction. Another thing for 3n's, which is kind of silly, is just you can do x equal 1 till x equal n, y equal 1 till y equal n, and z equal 1 till z equal n. So these are 3n things again, and everything is covered because, yeah. Planes are basically linear equations, yeah. So one thing I want to say is that at this point, when you notice these two constructions, you should already be pretty scared of this problem, because these are two very different kind of constructions. And if they're both working, there is something very magical going on here. Like, it's not usual for such problems to have multiple constructions that are totally independent of each other. And that already suggests the fact that you need to do something big brain here. Yeah, the weird equality cases, there is something going on. Yeah, also something worth, wait, oh, I think I have annotated. I don't know how I did that. It's clear all drawings. Wait, what? Guys. Okay, I think I'll stop sharing and reshare because I don't know how to fix these things. Okay. Oh shit, it's still there. What?
After that, could we review the constructions again?
Wait 1 second. I'm trying to figure out how to get rid of
Maybe
this.
the host can do something if we have a clear all option as well.
Wait, there has to be something I can do.
We could try to erase it
Yeah,
by
I'm
going
trying
back
to.
to it, right?
Maybe the host of the Zoom meeting can clear all.
I'm just going to close OneNote and reopen OneNote. That should probably fix it. Yeah, now it's gone. Okay, that was a interesting bug. I have never seen this before. Okay, yeah. So does anyone have any idea of how you could think of this in terms of polynomials? I mean, this is already kind of algebraic, and you have 3 variables. But the idea, okay, without spoiling too much already, is, I mean, essentially the kind of thing you want to do is you want to take ax plus by plus cz minus d, and you need to like product all of these things together, essentially. So what this would do is if you define, like, let's say, you know, the set of planes you're using is a1 x plus b1 y plus c1 z minus d1, a2 I'll just say m, b2 till bm, and c2 till cm, d2 till dm. Then you just take the product from I equal 1 to m of this
So
ai.
the least m such that combinatorial combinal doesn't.
Let's not think about the combo null yet. Let's just think about what is going on here. The point is that now, for example, we know that this polynomial whenever you take S1 as 1 to n, S2 as 1 to n again, and S3 as 1 to n, then this thing is 0 at everything in their intersection.
Well, shouldn't it be 0 for like 0, 0, 1 also?
Yeah. So that's the thing. We need to somehow add in that constraint. So the ideal thing to do would be to say this, but this is wrong because I mean now
X
0, 0,
plus
0,
Y plus Z should work, I believe. Then
the
we would
0,
have
0,
it
0
now.
thing is annoying us.
Like a factor of X, Y, Z or X plus Y plus Z could probably take care of that 0 issue.
So that's something we could do. Another thing that is quite common is we subtract something, which is again 0 at 1 to n, but non-zero at 0. So another thing like this. So I mean, for example, we could just take the product of these equations. So product x minus I y minus I, z minus I. So if you subtract this thing from this thing, it's still 0 at everything, but we can add some constant over here so that it becomes 0 at 0, 0, 0 as well.
Wait, I don't get why
But we
we
don't want it to be
subtracted.
0, right?
1 second. I'll just do this. So
Could you
you have
explain why we subtracted?
yeah. So you have this product which is 0 everywhere at this is kind of like Lagrange interpolation in some sense, but okay. But the point is basically you have something that's 0 almost everywhere, but non-zero over here, right? And you want it to be 0 everywhere. So what you do is you create another polynomial, which is again 0 here, and it's some other thing over here. And then you subtract it with the right constant. So you do this by this essentially. Very weird labeling. But basically you choose your constant so that, I mean, this was another thing which was 0 everywhere here, but it was non-zero. So when evaluated at 0, this thing is just minus n factorial cubed kind of thing. No, not minus. Okay, it'll be something weird, but it'll be some non-zero value. And then you can do 1 by that value into whatever is the value of P0 here. So to be more precise about things, I'll just actually write down the equation we'll use.
But don't want it to be 0 at P0, right?
You want it because you at the end, if you're using combo null, you want to say that it's 0 at everywhere when S1 is in this range, S2 is in this range, S3 is in this range.
Oh,
Wait, for we wanting it to be 0 everywhere, we have to think that we will be applying common and later.
Yes, so that's why this is a very hard problem, right? Especially given the fact that when this problem appeared, component was not a thing. Like, I mean, no one knew about it at least, right? So that really makes this problem like close to impossible, and that's why it's like a 50 moles problem or whatever. But
Is there any
I mean, we have to
alternate
solve
solution
the
for this problem?
Sorry?
Is there any alternate solution to this
No,
problem?
no, no. This is the same thing. I'm just showing some latex stuff just so that it's more understandable compared to like me writing things. Like this is AXYZ. This is what we defined first. This is the product of those things. K here is like M for us. This is the product of those things X minus I, Y minus I, Z minus I. And now you choose that constant so that it becomes 0 at A000 as well. Does this make sense? Because at 0, 0, 0, the value of this is A000 minus A000 by B into B000. So these two things cancel and this becomes 0. And at all other points, both of these expressions are 0. Because if x is 1 or something, then this is 0. And by the definition that we chose planes in a nice way, this is also 0. So basically now we have this nice polynomial, which is 0 everywhere on our set. So this is the usual strategy with combo null. You will first define a polynomial which you want to be 0 very often. And then you will check the constraints and you will get a contradiction. That's the usual strategy. You won't start with the degree and you will end up with the sets. You will start with the sets that you want to work with. So in particular, what is happening here? This is n+1 size. So basically T1 is n, T2 is also n, and T3 is also n. So first we need to check. So check 1 is degree 3n. Can someone tell me why the degree would be 3n of this thing?
It will be at most 3n, and that should be enough.
Yeah, it'll be exactly 3n actually because of this thing. Like what we're assuming basically is that m is less than 3n, because if m was equal to 3n, we already have a construction for 3n things. So if we have a set of less than 3n planes, so that everything is covered, then this first thing's degree is less than 3n, while the second thing's degree is exactly 3n. So the degree is exactly 3n. And that's pretty good. Now the other important question is, what is the degree of x to the n? What is the coefficient of x to the n, y to the n, z to the n?
Why did we consider B? Could
Just
you
minus
explain that
1
once
because
again?
the subtracting.
Sorry?
No, actually -1 into a of 0, 0, 0 by b of 0.
Consider B.
1 second. Why did we consider B? Again, to repeat, we wanted to use these sets 1 to n and everything, it was coming to be 0. The only problem was the 0, 0, 0 case. So the usual strategy in most of these sorts of problems we will see is that you take so if something is 0 almost always but not 0 somewhere, you take another such thing which is is always 0 always except that one thing, and then you subtract it with the in the right linear combination, so that now it becomes 0 at that place as well. Now another thing you could do here, for example, instead of using this was just an arbitrary choice actually. You could probably use something like x plus y plus z minus 1 into x plus y plus z minus 2. And so on, because this is till 3n. Because basically all we need is any construction we had, like any construction we chose here. We want to look at that construction. That's also 0 at all those things, but it's non-zero at 0. So we can choose the right linear combination, subtract them, and chill. The problem here would be this last step would not be very easy anymore. Like, it's not easy here to evaluate the coefficient of x. Wait, it is kind of easy. So maybe this is also equally doable. But yeah, whatever. The point is that all we really care about is that it should be something that also satisfies the same properties. So you can subtract this linear combination and get what you want. So yeah, what is this coefficient, by the way?
It's just a of o by b of o negative of that.
Yes, because the first thing, the whole degree is m, which is less than 3n. So that can definitely not contribute anything to this because this term has degree 3n. And this thing, you need to pick every x, every y, and every z to get this. So that gives you exactly 1. So that's just 0 minus this thing of 1. And both of these things are non-zero by the way everything is defined. So the coefficient is non-zero. And like, so we are done.
But the a of x, xyz can have degree 3n also. No? We have proved it less than.
Can have degree 3n, but then we're already okay. Like the point is we have a construction for 3n. Now what we're trying to prove is that less than 3n won't work.
Yeah, got it.
Yeah.
So what is the motivation behind picking just these A and B polynomials?
So A is, I thought,
A
pretty
is just
clear because
straightforward, and B is just you want it to be 0 at 0, 0, 0. So you just subtract a polynomial so that it's 0 everywhere. Because it's not nice if it's 0 everywhere except a point.
yes. Basically this is kind of a choice. You could have chosen another B. Basically any construction that you made yourself, you can choose that as your B and the proof will work. Like this was a construction we
Just a
had.
second.
So-
How are we done?
That's a good question. That's saying that we have degree 3n, we have this. So there should be something in S1 cross S2 cross S3, which is non-zero. But that's a contradiction to the fact that
It
we
is
define
0.
everything that was 0.
Okay, so
Alright.
the people who were actually giving the IMO, they were
Hmm.
supposed to figure out this whole thing about combo null, prove it in the exam, which mind you had been proven like 10 or 11 years prior to this problem, and then write the solution.
And note that people did it. Note
They
that there
did.
was someone who
They
did
did.
it.
Yeah, there was one person who solved the problem.
There
Somehow.
were 4 people who got a 7 on the 6th problem.
But
There were 4 people.
one thing I should mention is that proving combo null itself is not the hard part. Like if
No,
you can
how do you
get to this
think of
point,
combo null?
no,
Like
if
the conditions of combo null are like very, very specific.
yeah,
It's
no,
not
this
that
X to
specific.
the n, y to the n, z to the n thing is crazy.
It's like
But
finding a random point in a plane, whatever.
Like you don't think of it, you come up with it.
What's the
see,
difference?
this is the thing that you would do. Like basically what you would do is you would get to this point and you basically realize that this is kind of like a 3 variable version of the normal thing that you keep doing. That is, polynomial can't have that much degree. And then you actually need to do it. So what you would do is think of it as a polynomial in just x. Basically, first part of, you will not think of this coefficient being 1 plus 1. That part will not come to your mind at all. What you would think of is that, okay, the polynomial seems to have a bit too high degree in this variable, but is that really a problem for me? Not really, because I can keep fixing that. Oh, but what if it becomes a 0 polynomial? Oh, but it can't because this coefficient exists. So they need to it is very non-trivial to magically
By the way, if we all are losing our minds, why not just do 2007 P3 also?
What
What's
is
that?
2073? I forgot.
So
The
what
dot graph
I
theory
think
problem.
we have been shifted in.
play here?
Sorry?
I
What
think about
is the
so like,
contradiction in play here?
I couldn't hear that.
you have a bunch of a graph of friends and like
Oh
this
yes,
even
that problem.
yeah,
Okay.
The
I
math
have no idea
competition.
what is being talked about.
Yeah, let's not talk about that problem. It's not really.
the problem is not a problem, honestly.
Speaking
2007
about
was
hard
a very
IMO problems, since we've already gone off the tangent here, I was trying Turbo the Snail while walking, and I was so close to the solution.
What
Okay,
is turbo
let's
display
let's
again?
do one more interesting thing before we wrap up. Has anyone here heard?
Exactly is the contradiction in play here.
So again, to repeat the contradiction, these sets had size n plus 1 each. Your degree was 3n, which was this thing, summation of t1, t2, t3. The coefficient of this thing was non-zero. So by combo null, something in this cross product should lead to non-zero. But the way we have defined it forces it to be 0. Contradiction. So the
Like
contradiction actually is in this m less than 3n. What is realistically happening is that m's value is actually 3n exactly. And then when you do the subtraction, that 3n term
it
cancels
should be 0. Yeah, it'll become
and
0.
then the degree is not 3n anymore. So the degree becomes lower and combo null doesn't apply.
Oh
That's what's happening in real life. Okay. Has anyone heard of this problem? So you have a set, and this is a very natural kind of thing. What's the minimum, let's say the cardinality of the set is M. And you want a subset. It's not exactly very natural, but okay, actually I'll start with this. So you have a set of 5 elements. Prove that there exist 3 with sum divisible by 3.
Wait, what's the question?
What?
What's the question again?
Yeah, you have 5 elements, x1 to x5.
No,
You
like-
want to do the subset of sum 3 so that their sum becomes 0 mod 3.
Wasn't it like a DOS result which we were discussing?
Yes.
If mostly sum to 0, then each residual
Okay,
graph has
don't need to like prove it to me. I mean, this is just like pigeonhole stuff. Like
Yeah,
don't
yeah.
Oh, so
exclude.
we do combinal by
Case
taking
bash
the
just
3
works.
case called.
You can just
This
take
needs
like the
to-
elements minus 1 and then do it.
Yeah, that's
actually a
true.
neat solution
I'm going
without
to
case
change this
bash.
slightly. Your case bash becomes slightly harder, but it is still doable. I'm going to change it a little even more, and then your case bash becomes very, very painful, but still possible. And then I'm going to change this to general, and then you can't case bash. So this is the statement of Edas. Give bugs ziv.
Yeah, it does it.
Is it like R333M times?
Is it three important? Like the sum of three elements? Is that part important? Or
No,
there exists
that was just an example. The general statements. Sorry, you're right. Sorry, P elements. Sorry, I should have fixed that.
same P. It has to be same P.
Yeah. S with 2p minus 1 elements, there exists some p of them with some divided by p. P is a prime.
It's like the
Fact,
Cauchy
turns out-
Davenport thing. Somehow it's Cauchy Davenport.
Yes, this is literally an application of Cauchy Davenport.
Cauchy what?
Yeah, so basically Cauchy Davenport is a very nice theorem which can be proved with combinatorial Nullstellensatz. So we're going to prove this thing, which in turn will help us prove this. And the funny thing about this is Atul actually used this on a problem today, which also had a solution which noted that p plus 1 by 2 plus p plus 1 by 2 is greater than p. This was the intended solution, but he actually used.
What is Cauchy Davenport?
We'll just see that. We'll just see it. So
that's how I need to remember Cauchy Davenport. Like the first thing when I saw this is like Cauchy Davenport because of what Atul did today.
Yeah. I was like shocked.
Wait,
like,
where did Atul do this?
This was in some like Sophie team contest.
So like, when he said I didn't even know what the theorem was, I googled it up.
Yeah, I was like, I mean, I knew that it's used to prove this. I'd forgotten the exact statement. I was like, what the hell? And then I was like, oh.
I've seen the statement before in a combo null handout from the Canada stuff, but like I never knew it was called Cauchy Davenport. Like no one ever uses the name Cauchy Davenport. Like using the name is just crazy.
Yeah.
Now that I think of it, I think I've heard of that name in like some random Austria MO solution.
No.
So I remember Rushil giving it to somebody in camp.
Wait, who gave it to whom?
You gave it to someone. I think Sai and Shreyan, I guess, if I
Oh,
recall.
that's because there was a combo null class in camp, so we did. Yeah.
Oh, was it where like some of the junior guys just became seniors for a few days?
Okay, guys, we have limited time. We need to start this.
Right.
Okay, so you have A and B. These are okay. This
Sets.
is not the best notation I've ever had. Okay, it's kind of okay actually, but I'll just for sanity's sake, I'll just say 0 to p minus 1. And everything is mod p. So if you have
are they elements or sets?
They're sets. Oh, that's a good point. Thank you. That was very silly. Yeah. So the point is, okay, good question would be, what is this? This is just every pairwise sum. So sum of two sets is defined as x plus y, where x belongs to x and y belongs to y.
I'm assuming not to be used on an Olympiad without like saying it.
I think it's reasonably common notation for, let's say, IMO or TSTs, but I mean, it's literally takes 10 seconds to describe what the notation is, so might as well do it. Also, just it's nice practice, just for people. But yeah, the point, okay, also to be clear, everything here is happening mod p. So for example, if 0 belongs to a plus b and p belongs to a plus b, these are the same element. So the cardinality this will not count twice. This will only count once. Like, so I should just say everything over fp.
And you just say P and V are subsets of the P directly.
Yeah, I can, but I'm just trying to, like, just in case someone's not very clear about the notation. So yeah, this is a pretty cool statement actually, and it feels kind of obvious. It is obvious when you don't work mod a prime, because what you could do is like just order the elements. Like if you were in, let's say, the real numbers. So let's say you had a1 to am and b1 to bn. Then you have that a1 plus b1 is less than a1 plus b2, blah blah blah, is less than a1 plus bn, is less than a2 plus bn, is less than blah 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 am plus bn, and these are exactly m plus n minus 1 things, so you get this thing. But mod p, things go wrong because less than is not a real thing, and these two things could be the same, so you have no idea what is actually happening. But does this solution for real numbers make sense? I mean, it's not very relevant, but it's just to gain some sort of idea on why such a thing might happen. And actually you have equality. So if these were both arithmetic progressions, then this will be the exact set of things you can create. So it would give you exact equality in that case. Yeah. How is Rushil consistently saying Combinal's full form? Yeah. I don't know. Sometimes we're like,
I mean, like, it's just combinatorial Nullstellensatz. It's not too hard.
it's impressive. Yeah. Okay. So let's think about this. How do you think we could think about this in terms of component? Do you have any ideas?
X plus y is the product. You know, take product of the
Sorry, I didn't get you.
take the product of these.
Product of what? A and B? That's not exactly what we want, but that is kind of useful. Okay, so let's look at it like this, right? Let's say A plus B is C1, C2 till CK. Okay, let's just make some trivial observations. First, if the size of A and the size of B, if mod A plus mod B minus 1 is at, let's say if this is at least P, for example, then we should just be done by pigeonhole. So that's actually what Atul did on that problem, where, by pigeonhole, actually greater than P is where you can be very clear. If this is true, then you can create anything, because the point is, let's say you want to create some value C, then you take everything of the form C minus A where A belongs to A. So these are mod A different values, but there must be some overlap with the mod B values. Otherwise, we have a contradiction, because I mean, like, to be clear about this, let's say the set C minus A, I'll just use weird notation, set C minus A and B, let's say they have no intersection. That would mean that C minus A and B is cardinality, sum to less than P. The cardinality of C minus A is exactly the cardinality of A. So that's a contradiction.
I think you meant empty set and not
Yeah.
zero.
Sorry, I've been doing too much linear algebra. That's the only time you do that. Okay, I noticed that. Okay. Anyway, so let's say A plus B is C1 to CK. And the trick is now going to be to look at something like X plus Y minus CI. Something like this, some product of this form. So what exactly are we looking at here? So the point is that if you take everything in this product, so like just C1 to CK, so I1 equal to K, and choose X from A and Y from B, then this is 0. Because literally the way A plus B was defined, there must have been some X in A and some Y in B, so that X plus Y was equal to this element. So there is something that goes wrong. Like, as in, basically, if this is non-zero, then that means that X plus Y does not belong to C1, C2 till CK. So then A plus B has some extra element, which we didn't talk about earlier. So assuming that it doesn't have such an extra element, we would have that the thing is 0. And this is already like, we're halfway there. Like this is like, if you have T1 plus 1, T2 plus 1. So now you need to check degree T1 plus T2. So basically you want to check that the degree here is mod A plus mod B minus 2. And that's true, because if this set had size at least mod a plus mod b minus 1, then we are already done. So we are assuming that the size of the set is less than that. So it's at most mod a plus mod b minus 2. But in that case, the degree is at most mod a plus mod b minus 2 because we're taking a product of k things, and k is at most mod a plus mod b minus 2. And given that that's working out, the degree is fine. And now we need to check x to the t1, y to the t2. So that in our case is x to the mod a minus 1, y to the mod b minus 1. And notice now this is kind of important. You don't want just the fact that the coefficient is non-zero. You want the coefficient to be non-zero mod p, because everything we have done is mod p. So this is equal to 0 mod p.
So if you get some sort of symmetry and you can say that it comes up p times or something, then you'd be done anyway.
No. Then you would be not done because you need it to be non-zero.
Right.
You don't want it to come up.
Then you'd be like cooked.
Yeah, then you would be in big trouble. Okay. So yeah, now you actually want to exactly evaluate this. And yeah, so the way of doing that is just like assuming, so if the size of the set is okay, actually we need to make an assumption that there are mod a plus mod b minus 2 things. Because if not, basically let's say the degree
Why
was
can't
mod.
you just say k is smaller than p? If k is bigger than p, we are done, right?
Yeah.
We can just say k is smaller than p, and then we
Yeah,
don't have to
that is
worry.
fine. That part is anyway done. And the second part that we also have to assume is that the degree is exactly mod a plus mod b minus 2. If it's not, then we'll run into some issues. But in that case, basically we can say, okay, I'll just add a new term to make the degree exactly equal. Like I'll just add x plus y minus 0. Do what you want. So basically, I'm going to force the degree to be exactly that. The reason I'm doing that is I need a term of this thing. Like if the degree is less than mod a plus mod b minus 2, then the coefficient here will obviously be 0 because the degree was too low. So I need to artificially make the degree at least this much first. And once I've done that, then the degree will be exactly mod a plus mod b minus 2, choose mod a minus 1, mod b. This is just binomial theorem, like, because basically there'll be exactly mod a plus mod b minus 2 brackets. So if you ever pick a constant, you can't get to the max degree thing. And then you need to choose mod a minus 1 out of those things. And then you need to check that this is not 0 mod p. But that's fine because by our assumption, this is at most p. Otherwise, we are already done by like pigeonhole. So if this is at most p, then this is looking like p minus 2 choose something. But if your factorial is like p minus 2 factorial, where will you get the 0 mod p from? Like this thing is never going to be 0 mod p, right? Because it needs to be at least p factorial for that to happen. Okay, so that's a very random thing. Now it's for you guys to figure out where exactly does this come into this. It's actually a very neat proof even now, but it's now you just need like nothing. Now you just like do something smart and it will work out. But yeah. Okay. Does anyone have any questions with anything we did today, or like in general?
Have you ever come across a readable handout for Nullstellensatz?
So
Okay,
if
for the
you
first
remove the word readable, yes. If you add in the word readable, not really.
comprehensible.
Surely
There are
write
a
one.
couple of there are a couple
Surely
of
write one. Like I feel like a lot of people would like a readable one. So
there are a couple of things that you should be able to understand now. The fact that you've seen this lecture, and
yeah.
if you understand today, then you should be able to understand most things in a handout. I think, yeah, I mean, I don't like. In fact, it was actually going to be a chapter in my book, by the way, Combinatorial Nullstellensatz. It was a chapter till very long, but it got removed because I just didn't want to do algebra. Like this feels like algebra first combo later.
Yeah, it was A7.
Yeah, but also like even though the idea at heart is combinatorial, I would need to get into a lot of algebra. Like I would have to talk about these degree things and all that, which I don't really want to do. Like I don't mind doing that in general, but not in a combi book. So I
Wait,
didn't.
so what happened to generating functions?
Same reason. No one
Oh,
likes
so
it.
it isn't there.
Yeah,
So
it's
I
not
don't
there.
have the book yet. So
Okay, I see. The
Because
generating
Jagger,
function does not deserve to exist in my book. It's cringe and it should not exist.
No,
some
GenFunk
generating
is
functions
nice,
are
right?
nice. Some
GenFunk
gen
can be nice depending on the application. Like I've seen some really cool GenFunk
Okay,
applications.
it's only nice when the solution is one line using it. Any more
Yeah,
than that?
No. This
it's
is what
only nice when the solution is one line and you get to do ROUF.
ROUF full form.
Okay, I'm going to just like stop recording. By the way.
Oh yeah, that's a good call.